Good morning. This is the sixth lecture of CEE. And before I start, I would like to apologize for my missing of the last lecture. It was due to some, let's say, stupid factor. So I put in my mind that the class was at a different hour than what it was. Okay, so let's start. Today I would like to do two problems. Okay? We have been speaking about the solution of the homogeneous equation. So let's go. This equation, x dot equal to ax with some initial condition. And in the case, we have shown that in the case where the matrix A has n independent eigenvectors, then you can express all the solutions as a sum of these terms. It's a coefficient that depends on the initial conditions, an eigenvector, and the exponential of the corresponding eigenvalue times time. And you do this for all the eigenvectors. Okay? Now, we have proved this only for the case where you have n independent eigenvectors. So these terms are linearly independent for all times. You can show that. And in the case where you don't have n independent eigenvectors, you cannot span all the space. So in that case, you need to add some terms that correspond to the exponentials multiplied by time polynomials. Okay, and for that, use the so-called Jordan canonical form, which is out of the scope of this course. So we are going to consider just this situation. And each of these terms, remember, it's called a mode because it corresponds to an oscillatory mode. We have seen one example of a second order case. And now one of the problems I want you to solve, okay? I can solve it with you, but I would like to pick up your notebook and to solve it by yourself, is this. So I give you four matrices. These four matrices, A1 to A4, written here. And I give you four phase portraits. So the trajectories, the orbits, the solutions of the state in state space when time progresses. You start from some initial condition and you move along these lines. And the question is, which matrix corresponds to which phase portrait? Okay, this is a quite important problem to understand. And my suggestion is compute the eigenvalues, and in some cases you will need the eigenvectors, but start to compute the eigenvalues for all these four matrices. And then remember that this is a second order system, or these are second order systems. So xt is a linear combination of two modes. In this case, you will have two independent eigenvectors. So you can write the solution as k1 v1 exponential lambda 1t plus the same for the second mode. Okay? So remember that if lambda is real, then you have a real exponential. You don't have any oscillations. If lambda is negative, real and negative, then this exponential is decreasing, and you are approaching the origin. If lambda is positive, you are going away from the origin. Now, if you have a complex number as eigenvalue. It has a real part that corresponds to a scale factor. And depending on whether the real part is positive or negative, you are expanding or shrinking. And then you have an imaginary part that corresponds to an oscillation. Okay? If you don't have any real part, or if the real part is zero, better to say, then you will have just the exponential of a pure imaginary number that varies with time. And this corresponds to a pure sine and cosine, so you will have some oscillation. So start by computing. I will give you some minutes to compute the eigenvalues and the eigenvector, the eigenvalues of these four matrices. Then, in some cases, we are probably going to need the eigenvectors as well. So start to compute the eigenvalues. Let me make you remember one thing. I'm sorry, I will have to connect my whiteboard.
Professor, pode voltar a partilhar a tela, só se favor.
Vou já, estava só aqui a montar aqui a...
Certo, obrigado.
Só um momento. Já vou partilhar a tela anterior. So let me remind you before, I will show again the matrices, but before that, remember this. Suppose that you have a matrix A. So you can compute the eigenvalues as the determinant of lambda I minus A equal to 0. This is the characteristic equation. Okay? So let's start with the first matrix. So we have A1 is equal to 0, 1 minus 2, 0. Okay, so compute the eigenvalues of this. The eigenvalues will be given by the determinant of lambda I minus A1, which is lambda minus 1, 2, 0, and this is, sorry, 2, 0, no, 2 lambda. So this is lambda square plus 2, okay? And the eigenvalues will be, in this case, lambda 1, 2 equals 2. Who helps me? Quem é que me ajuda? You equate this to 0. So what are the roots of lambda squared plus 2 equal to 0? It's lambda square equals to minus 2. So lambda is equal to
plus and minus j
plus minus j
root square of
square root of 2. Okay,
square root.
so you have two eigenvalues, one here and one here. Okay, so this was just the first example. I did it by myself. I did it for myself, just to show by myself, to show you okay, can you see it now? So I did the first example just to show you how to recall you how to compute the eigenvalues. Now compute the eigenvalues for all the matrices. So I will give you some minutes. If you want to ask me something, please feel free to ask. Podem perguntar em português. Can you raise your hand when you are finished the computation of the eigenvalues? Thank you. Some more minutes. Those of you who have finished to compute the eigenvalues will notice that there are two cases in which the eigenvalues are the same. So think a little bit, how can we discriminate between the matrices and the figures, the pictures? will go for a moment to the whiteboard. So for instance, for A2, I'm sorry. Can you see the whiteboard?
Yes, you can.
Yes.
Okay, so A2 is 0, 1, 1, 0. It's, and so I have lambda minus 1, minus 1, lambda. So this is lambda squared minus 1 equal to 0. So I have lambda 1 equals to 1, lambda 2 equals to minus 1. Okay? And A3 is equal to let me see my notes because I need some notes. In a normal classroom, we would have the blackboard. So 0, 1, 0, 1, minus 2, minus 0.7, and this gives you lambda, lambda plus 0.7, minus 1, 2. So this is lambda squared plus 0.7 lambda plus 2. And of course you can solve this equation if you equate this to 0 using the formula for the solution of a second order polynomial. And this is lambda 1, 2 is equal to, here I put a 2, 0.49, that's 0.7 squared, plus or minus sorry, this is not 0.49, this is minus b. Minus 0.7, and here b squared, so 0.49, minus for AB, so minus 8. Okay? So the eigenvalues in this case, where are they located? Who helps me?
In the left plane.
In the left plane. Why?
Because of the minus 0.7.
Yes. Well, there is one critical thing, which is this stuff here.
Yes, and the imaginary part.
This is the imaginary part because you have 0.49 is smaller than 8, so this is a negative number. So you have the square root of a negative number. So this is just imaginary part, and this is the real part. So it will be 1 here and 1 here. Okay. A second order polynomial, it's necessary and sufficient to have the roots in the left hand plane if the coefficients are positive, which is this case. Okay, so we could have written this right away. And A4 is equal to 0, minus 1, 0. So I have lambda 1, 1, lambda squared minus 1 equal to 0. So again, I have lambda 1 equals to 1 and lambda 2 equals to minus 1. Okay? So take care of this. We have a problem because A2 and A4 have the same eigenvalues. Okay? Any doubt about how to compute the eigenvalues? I could have also written A minus, I could have also computed A minus lambda I, because I'm equating this to 0, so it's equivalent. I would get the same numbers. Okay, so I will stop sharing this. Maybe we will have to return, and I will go to here. Now, which is which? The low, start by picking the low fruits. Comecem por apanhar as maçãs dos ramos mais baixos, quer dizer, resolver os problemas mais simples. For instance, sorry?
I think the A1 matrix corresponds to the D.
So you're saying that A1 corresponds to D. Why?
Because it's just imaginary poles, pure imaginary poles.
Pure imaginary poles. So if you have pure imaginary poles, you have an exponential of a pure imaginary number, which is cosine plus J. J is the imaginary unit times sinus. Okay, and remember that you have two terms, two conjugate terms. In the end, you will have just a real oscillation, but it's an oscillation. You don't have damping. So the poles, or the eigenvalues, sorry, better to say, the eigenvalues of A1 are pure imaginary. You have an oscillation, which is here, corresponds to closed curves. Any question? No questions? Okay, now another case which is simple to say.
I think that A3 corresponds to the third one. So we have
A3 corresponds to C, to this third one. Okay, why?
It's a damped oscillation, so that's what you see there in the diagram, basically.
So I have eigenvalues in the negative left plane, in the negative plane, complex conjugate. This corresponds to a damped oscillation, so you are curling and spiraling towards the origin. Okay? So that's true. And now we have these two ones, these two. In these two cases, we don't have any oscillations, but we have changes. We have exponentials composed. Now, how can we discriminate between these two? You can look at the eigenvectors. Let me show the next slide. Okay. Suppose that these are the directions of the eigenvectors. Okay, consider this case, and the eigenvectors are associated to eigenvalues. So, if you start aligned with an eigenvector, suppose that you start, look at this formula here. Suppose that you start aligned with the eigenvector number 1. What can you say about K2? So the coefficient associated to the other mode, to the other eigenvector. So for t equal to 0, okay, for t equal to 0, you are aligned with V1. So what happens? How does this simplify for t equal to 0? You get x of 0 is what? Is K1, some K1, times V1, times what?
Yeah. Times 1.
Times 1. So you have K1 V1 plus K2 V2. So what can you, if you start aligned with V1, what can you say about K2? The coefficient of the other eigenvector, of the other mode, better to say. Is big, small, medium size, can't say anything. Look, you don't have to know anything about dynamic systems or differential equations. It's just factors. You know that x0 is proportional to V1. Okay, so if x0 is proportional to V1, K2 has to be 0 because you don't have any component associated with V2. Okay, if you start aligned with an eigenvector, then you will stay aligned with that eigenvector because this K2 is 0 and this term is not there. And the solution is just K1 V1, the exponential of lambda 1t. Could you understand this? Some of you understood, some of you did not understood.
I didn't understand it.
Okay, so let's go to the whiteboard. Where is the whiteboard? Okay, so stop sharing, start sharing in the whiteboard. I would like to have 2 whiteboards. Can I clean this thing?
Yes.
I can, I will clean it here. I will also clean this part here. So what I'm going to say now is just geometry. It's just geometry, okay? So suppose that you have your system of coordinates and you have 2 vectors. One is this vector. Okay, I call it V1. And then I have another vector. Let's write it in, which is, let's say, this one. V2. Okay? Now, suppose that I start with a point which is aligned with V1, say here. Okay, so I call it x0, and I'm aligned with V1. So I can describe the point by a vector. Okay, I can describe this by a vector. So x0. Now, x0 is a linear combination of V1 and V2 because V1 and V2 are independent. You agree that V1 and V2 are independent. Everybody agrees? Or is there anyone who disagrees? So V1 and V2 are independent. So I can express any vector as a linear combination of V1 and V2, right? So I say that x0, any x0, not only this one, but wherever I could place it, would be some coefficient, K1, V1 plus K2 V2. And K1 and K2 depends on X0. Everybody agrees? Is there anyone who does not understand this? So there are always K1 and K2 such that I can express any vector in the plane as a linear combination of V1 and V2. This is V2. Okay? Now, consider now the case in which you are aligned with V1. What can you say about these coefficients?
K2 is 0, as you said.
K2 is 0 because you don't have any component along. If my X0 was, for instance, here, okay, I would have a component in this direction on V2 and a component related to V2, sorry, a component, this one, related to V1, and this other component related to V2. But if my point is over the direction of V1, then this component is 0, and so this is 0, and this term is not there. Okay, is this understand?
Yes, yes.
Okay, now what happens is exactly what you have in, is exactly what you have in the dynamical system case. So in the dynamical system case, you have that xt is K1 V1 exponential of lambda 1 t plus K2 V2 exponential of lambda 2t. Okay? And depending now, what is the initial condition? The initial condition is something which is x0, is make t equal to 0, so it's K1 V1. Now the exponential becomes what? When you make t equal to 0, becomes 1, so the exponential of 0. So you don't have it there, plus K2 V2. Okay? Now, suppose that you have both components, x1, x2, and you have these vectors. Suppose that you have this vector here, which is V1. And you have a vector here, which is V2. Okay? Now, you start, if you start a line here, then for this point, for the solution corresponding to this point, starting in this point, it will evolve. But you know that in the beginning, at the time instant 0, K2 will be 0 because you don't have the component of V2. So this is 0. Okay? So this point will be such that you have xt is K1, V1. K1 depends on this initial condition. I mean, if you start here, you have one K1. If you start here, you have another K1 and so on. But now you have that time, that term, lambda 1 t. Okay? And you don't have the other. Why? Because K2 is 0. So when time changes, yes.
Why is K2 0?
Because of you started aligned with the initial condition, with the vector V1. So for t equal to 0, these coefficients, they only depend on the initial, on the initial conditions, okay? So if you start aligned with V1, you agree that K2 is 0.
Yes.
No, K2 is the same when you write the formula for general time, is the same K2. And if you start here, K2 is 0, okay? So this term is no longer there, which means that where are you going to move? Can you move, for instance, in this direction? Or in this direction, or in this direction, or in this direction, or in this direction? Which one? 1, 2, 3, 4, 5, 6. Where are you going to move? 7. Tell me one number.
1 or 4.
1 or 4. So always aligned with V1. Okay? So you don't move to the others. You don't move outside of this direction. So it's 1 or 4. Now, what makes you go away from the origin, that is to say, towards 4, or towards the origin, that is to say, towards 1? What makes you take one way or another way? So going away from the origin or going to the origin?
The signal of K1?
The signal of K1, well, not exactly, because K1 depends on the initial point. It does not affect you, the movement. There is something that has to do with time.
The signal of the eigenvalue?
Of the eigenvalue, okay? So if the eigenvalue is positive, what happens to this exponential?
Goes to infinity?
If lambda 1 is negative, does it go to...
No, if it's positive, goes to infinity. If it's negative, goes to 0.
So if it is positive, where am I going to move? 4 or 1?
4.
4, I'm multiplying by a number which is bigger and bigger and bigger, so I go in this direction. So this is if lambda is bigger than 0. If lambda is smaller than 0, then I go to the origin, because this is shrinking my x. Okay. Questions? So the final root is very simple. Over the directions for the states, the initial states that are aligned with the eigenvectors, you always move along these directions defined by the eigenvectors. If I started here, what would be the initial gain, those gains, K1 and K2, if I start here?
K1 would be 0 and K2 would be
different from 0, anything. Okay. Okay. So suppose, let me suppose that, let me clean this a little bit. Where is my eraser? So suppose that you have V1 and you have V2, and suppose that lambda 1 is negative and lambda 2 is positive. Okay? Now, suppose that you start here at this point. Where are you going to move? I'm aligned with the direction of the eigenvector, so
towards the center.
And I will move over the eigenvector towards the center, so I'll move in this direction here. Suppose that I start here. Where am I going to move? This is tricky. This is again the direction.
So
Yes,
I think the direction towards the center will remain.
Yes, that's right. So I go in this direction. Okay? Now, suppose that I start here. I start here. Where am I going? At the blue point. Lambda 2 is positive.
To infinity.
To infinity following the eigenvector directions. Okay? Now, suppose that I start here. Say, it's again this direction, but I start here. Where am I going to?
Down. You would go down.
Down to infinity. Okay? Okay? Now, suppose that I start here. So close to V1, but not exactly over V1. What happens?
It would go to the origin, but trying to follow the vector V1.
So you have two components of the movement. One component forces you to go in the direction of the eigenvalue and approaching the origin. But then you have this other component, which is in the direction of V2, that forces you to go away. Okay? So you will do something like this. Okay? What about if you start here? Down, left, up, diagonal right, diagonal left, diagonal down, left. Where? Again, I have this component and I tend to move along that. But then I have this other component that is increasing. So I will have something that increases. So I do like something like this. The plot is very bad, okay? Okay?
Okay.
So let's go back to our figure. Let's go back to our picture. Okay, so we have to discriminate. We have these two matrices, which one were A4, and A4 and A2, no? A4 and A2. Okay, so you know that A4 and A2, they correspond to these two pictures here. Let me enlarge it. So what are you going to do to find which is which?
Check the directions of the
Eigenvalues.
asymptotes.
Of the eigenvectors.
Yes.
The eigenvectors define asymptotes. Portanto, verificar as direções dos vetores próprios que definem assímptotas. Okay? So compute the eigenvectors. Now, computing the eigenvectors, usually it's a little bit tricky. But you can start. you know that lambda I minus A VI. VI is the eigenvector associated with eigenvalue lambda I. This is 0. Okay, now you have, this gives you two equations, but since the determinant is 0, you know that these equations are linearly dependent from one from the other. So you have two unknowns and two equations. So use just the first equation. So I have lambda VI1 minus 1 times VI2 is equal to 0. And this is lambda I. Now you choose VI1 to be 1 because you have two unknowns. So VI2 is equal to lambda I. Okay? So if you have, in this case, lambda 1 is equal to 1, and V1 is the first component I selected to be 1, and the second component is lambda I, so it's also 1. And lambda 2 is minus 1, so V2 is 1 minus 1. Okay? So what do we have? What do we have? What do I have? I have x1 and x2. Now I have the eigenvalues, which is 1, 1. So one direction is 1, 1. And along this direction, the eigenvalue is positive. So am I approaching or going away along this direction?
Going away.
It's positive, so it's going away. Something like this. And the other one is 1 minus 1. So 1 minus 1. I have this direction. And along this direction, the eigenvalue is negative. So I approach. So I will have something which is something like this. It's called saddle point. Okay? Because these are like the trajectories that you would follow in a saddle, a horse saddle. Okay? So what is the solution? What is the solution? So this was for A2. And if you go to you are looking for something that moves away in this direction. Actually, the eigenvalues, the eigenvectors are quite similar. It goes away in this direction and goes to the center along this direction. and this corresponds to A2. So A2 is B, and A4 should be A. Okay? Any question?
No, professor.
I have one. Just why does the C1 go towards the middle? Is it because the real part is negative?
Why does the C1? What is the C1?
The C graph.
In this case, it's because the real part of the eigenvalue is negative.
Okay.
So you have a real part and an imaginary part. The imaginary part makes you go round, okay? But then the distance is decreasing because you decompose this exponential as the product of two exponentials. One is a real exponential, which is negative. So it's something that is decreasing. When time increases, the exponential of minus something like time decreases. And then you have an exponential, which is a pure imaginary, like this one. So you have, one is forcing you to have a cosine and a sine, so you are going around. And the other is shrinking. Was it clear?
Yes, thank you.
Okay. More questions?
Professor, and if we add like a positive real part in those
it would instead of approaching the origin, it would go away
with the same form.
Yes, it's an oscillation in time. It's an oscillation that grows and grows and grows and grows. The amplitude is growing.
Okay.
Instead, here it's something. The oscillation is decreasing. The amplitude of the oscillation is decreasing in this case.
Okay. Thank you.
Okay.
I have another. If we had two eigenvalues positive, would it be like a kind of a star?
No, it's like do you like fishing? É como um anzol, forma ali um anzol. Eventually, you can do a turn, but you don't have oscillations. Let me see if I have a plot here. No, I don't have it. But if you give me a moment, I can include this slide here later. But I can pick it up somewhere else. If you give me one moment. Can you see this slide? It says classificação da dinâmica around, okay? Can you see? Okay, so you see that if you have the position of the eigenvalues and qualitatively the type of state evolution that you might expect. Okay, so if you have two eigenvalues with negative real part, complex conjugate, then you will have something that turns towards the origin. If instead the real part is positive, they turn, but they go away. The amplitude of the oscillations is increasing. If you have two, this is called a focus, a stable focus and an unstable focus. If you have two negative and real eigenvalues, you might have something which is, you have a turn, but you don't have oscillations. We call this a node. Okay, so you have this type of response. You have the stable node and the unstable node. Okay? If you have,
then the shape depends on the eigenvectors, right?
Yes, yes, it will depend on the eigenvectors, but it's difficult to say exactly from the eigenvectors because you don't have asymptotic points, asymptotic direction, sorry, here. If you have pure imaginary, you have this ellipsis, closed trajectories. If one is positive and the another is negative, then you have the so-called saddle point, which was what we had been selecting. Okay. So by having computing the eigenvalues, and in the case of the saddle point, so the saddle point is the only one which is for which the computation of the eigenvectors is important. Then you can have an idea of the qualitative way in which they turn. Now, one thing is, am I turning in clockwise or counterclockwise? Okay, how can you see that? You see, let's see a specific example. Let's see a specific example here. In this case, am I turning clockwise or counterclockwise? So this was associated with, I think it was A1. Yes, it was with A1. So, okay, how do you think you can see that you should turn counterclockwise or in the clockwise direction? No ideas? So let me go again to the whiteboard. Let me clean everything.
Could it be with the values of K1 and K2?
K1 and K2 depends on the initial condition, and you can start in many points, virtually any point. So K1 and K2 do not help you in this case.
Okay.
But where do you go at some point? What is the thing that tells you where you go at some point? Now, let me write the equations. Let me write the equations. So we know that we had x1 dot and x2 dot is equal to 0, 1, and minus 2, 0. x1, x2. So you have the equations, which is x1 dot equal to what? Schnell. Rápido, respondam rápido.
X2.
X2, good. And x2 dot is equal to?
Minus 2x1.
Minus 2x1, okay? Now, suppose that you have your phase, your space, state space, x1 and x2. And you are, say, for instance, at some point, where you go at some point. You know that you are going around, but what is the information, the simple information that tells you where you go at this point? If you are at this point with coordinates x1, x2, general coordinates, sorry. Suppose that you are at this point. x1, x2. This specific point, say 2, 3, or whatever you want. Where are you going? You are going to move in some direction. Where are you going to move?
Up and left.
Why? What is the thing in the differential equation that tells you that?
The signal of the derivatives.
The signal of the derivative. So you are going to move in the direction of x2 and minus 2x1. So this defines a vector, I don't know, point somewhere else. So for this, suppose that x1 is, say, 2 and this is 3, then you are going to move in the direction defined by 2 minus 6. So here, 2 minus 6, you are going to move in this direction here, not there. Okay? Remember, this is the so-called field of the differential equation that tells you where you go. Your curves are tangent to this. Now, is there, and this corresponds to the derivatives. So your colleague was saying, well, they're both x2 and x1 are positive, so x1 is increasing and x2 is decreasing. So that's the reasoning of your colleague. Now, is there a point where it's very easy to compute these directions?
The imaginary axis where there's no real component, the real axis where there's no imaginary component, like the
okay,
where it
so
crosses.
let's pick up. Remember that this is real, okay? X1 and X2. This is not a seed plane. This is R2.
Yes, sorry.
Okay, this is R2. Don't get confused with a plane where you have the eigenvalues, which is C, the plane or the complex plane, and this is R2, so vectors in 2 dimensions. Okay, they are both real. So, but we could your idea was a good one. If I pick up this here, I know that the second component is 0. So here, for instance, x1 is something positive, and x2 is 0. So where am I going to go? So x2 is what? These equations, read these equations, x2, so x2 is 0. And the other is minus 2x1, whatever x1 is, but we know it's positive. So where am I going to? So x2 does not change.
You are going down because x2 is decreasing.
Okay, I'm going down. What about here?
The signal of x1 is negative, so negative with negative it's positive, and then it's increasing, so it's going up.
Okay. What about here?
Right.
X1 is 0, so x2 does not change, means that if x2 does not change, I'm going parallel to x1, that's right. And then x2 is positive there. Sorry, here x1 is negative, so x2 is positive, so x1 is increasing. Am I going to the right or to the left? X1 is increasing, so right. So here I go to the right. Okay, so you can use the sign of the derivatives to go to see where you're going. Okay? So with these two information, eigenvalue and eigenvectors on one side, and the sign of derivatives. Later, in the nonlinear case, equilibrium points and linearization about equilibrium points, you can sketch the evolution of your state in a qualitative way, just to have an idea. And this is a quite powerful method, okay? So the next, I was planning to do two exercises today, but we explored this, and I think that we did not waste our time because we have been going through carefully with these ideas. The next problem is to apply this idea to explain what happens at the Battle of Waterloo. Okay, what do you know related to Waterloo?
The fall of Napoleon.
The fall of Napoleon. I was expecting the music by the ABBA. So I will discuss the Waterloo battle based using these ideas on state and eigenvalues and eigenvectors. Poor Napoleon never thought about it. And I suggest that to do a preparation, you pick up the music from the ABBA and you listen to it, okay? Any questions?
Okay. No.
It's a good exercise for the weekend. Okay, so we see each other next Tuesday at 8 o'clock in the morning, and I will be there. I hope you will be too. Thank you.
Thank you,
Professor.
Have a good weekend.
Thank you.